Let's take a few minutes here to go over friction. Again, this is a composite force. That's just the interaction of all of the molecules in an object interacting with all the molecules of another object. So friction is a contact force that acts parallel, to two surfaces and opposes their relative motion. And two factors determine the magnitude: the roughness of the surfaces and how hard the surfaces are pushed together. So I think these kind of intuitively make sense, right? If something's really smooth, the friction's going to be lower. If something is really kind of pushing down on another object, you're going to get better friction between them. So if you have like a piece of sandpaper and you really push with it, you're going to be able to cause a lot of friction. And the reason for this is you kind of have this, when you zoom in, the surface of an object is kind of bumpy, right? Because it's not perfectly smooth. There's different atoms and they don't, all line up. And something that looks really bumpy, you can easily imagine how this is. If something looks really smooth, though, it's hard to imagine, but on a microscopic scale, you have something like this. Then if I have another object, it's kind of, shaped, say, something like this. And then you have all these parts where you got these two little bits here. They bump into each other, and they cause it to slow down as it's moving across. And eventually, if we bump enough times, that'll kind of take all the energy away and we get the object stopping. So that's how friction works kind of on the microscopic scale. If we want to calculate friction, we use the equation that F friction, there's actually two equations here. One is going to be less than or equals to mu s times Fn. And the second is force of friction is equal to mu k times Fn. This, excuse me, is the Greek letter mu, and it's the coefficient of friction. This basically is a rough way of describing how rough the two surfaces are. And we always talk about it as two surfaces. You might have the coefficient of friction of wood on metal, or rubber on ice, or rubber on asphalt. So you're always going to have two, it's basically the compared roughness of the two surfaces. The reason we have two is we have mu k, which is the kinetic, and this is for moving objects, so moving or sliding objects. And then we have mu s for static, and that's for stationary objects. And this is because they change as time goes on. So if we imagine again my hand against my face, if I start dragging my hand downward, it's not going to move initially, because what's happening is as I pull harder, the static friction increases up until I reach this maximum amount that my hand can kind of be held against my face, and then it starts sliding. And at that point, we have a constant friction that opposes that motion. Now, why are there these two? Well, because as we said earlier, if you imagine kind of zooming in like this, and then imagine kind of zooming in like this, then if they're stationary, those bumps have kind of a chance to settle in and kind of lock together per se. And so then if you start trying to move this top piece, then it's going to be very hard, because they're getting as much friction as possible. And these will oppose and oppose and oppose until this top piece is able to kind of slip out of those grooves, and then it's kind of bouncing along the top of the grooves and kind of bumping just the highest points as opposed to more of that. That's a real rough hand wavy way to explain it. If you want to go over it in more detail, let me know and we can talk about it. Then the other piece is this Fn, and this is how we depict normal force. And this is how tight the surfaces are pressed against each other. And this is typically proportional to the gravitational force, which we're going to depict with Fg, which remember is mg. And this is because typically we're talking about an object sliding across the ground, so the normal force is whatever's being required to hold the object from falling through the ground. So let's look at an example here. How hard would you need to pull a 65 kilogram skier for them to move at a constant speed across the snow? Assume the coefficients of friction are 0.4, 0.14, and 0.1 for mu static and mu kinetic, respectively. So now, if we're pulling them across the snow, that means that we are moving, so we're going to want to look at mu k. So let's draw a free body diagram for this situation. We know that basically always we're going to have this downward force of Fg. And that's because we're always going to be near the Earth, so it's pulling down. Now I know this skier isn't moving up or down, so I also know they have to have some upward force that's equal in magnitude, and that's our Fn, because the ground's pushing up on the skier. Now it's asking how hard I would need to pull, so that's my force in question, so F question mark, to oppose a frictional force backwards, and we know that these are equal. So I know those are equal, I know that those are equal. So now we know that, like I said, Fn equals Fg equals mg, because again, the skier isn't moving up or down, because they're moving across the snow. So their vertical forces have to be equal by Newton's first law. Then we're moving them at a constant speed across the snow, so we know also by Newton's third law, sorry, there should be a negative in there, that negative F friction has to equal the force that I'm trying to solve for. So the force that I'm trying to solve for is negative force of friction, which is negative mu times Fn, and then Fn is negative Fg. So I have negative mu times negative mg. So I know that my force has to equal mu mg. So if we plug in our values, I get my force is equal to mu is 0. I'm sorry, this should be k. So 0.1 times mass of 65 kilograms times g of 9.8 meters per second squared. And we're getting a number of, that's going to be roughly 65 newtons. Not exactly, but roughly. Now you'll notice the static friction and the kinetic friction, they don't have units, and that's because they're a ratio between the normal force and the frictional force. And we just get those by putting two objects together and seeing what the frictional force is compared to the normal force. So we determine those experimentally. Let me know what questions you have about this, but otherwise we'll jump forward.